Draft Science video. I think we'll put it on the Draft Science channel this time. I think so. That'll be the intention. See how it works out. So I'll deal with some of the comments first, I suppose. Still arguing about Feynman and the model. I really don't care anymore. So yeah, I'm really not interested in arguing Feynman's whether he did or didn't imply this, that, or the other thing too much, or say this emphasize what too much and emphasize something else too little. I'm just saying he does seem very glued to this probabilistic nature of the matter rather than recognizing that the probability is a byproduct of some sort of cause and effect. He didn't use the words cause and effect very often, and I suppose those are very important words in this subject of physics, in my opinion. Anyway, doesn't matter. QE has been born in hundreds of experiments. With QM, without QM, we would still be living in the 19th century. Prove it. Show me what QM invented. I'm sorry, quantum mechanics has not invented much. Okay, I mean, computers, transistors, all that stuff would have been invented anyway. All of this stuff that seems very physics related is basically stuff that's borne out through experiments, and experiments where you didn't need quantum mechanics to do the experiments. It's finding the properties of things. Quantum mechanics hasn't invented anything. It's facilitated invention, I would imagine. The math does make it possible to anticipate things, to figure out things, but there's lots of other math that we have regarding thermodynamics that is probably more relevant to modern invention, because the real problem with miniaturization is, getting rid of heat. But anyway, moving on. I don't know why you always try to pull it down. I'm not trying to pull it down. I think quantum mechanics is perfectly satisfactory modeling hardware. It's perfectly useful as a mechanism for it's obviously perfectly useful for breaking down a phenomenon that's taking place and being able to predict, I think is a silly word to use, but yeah, to run efficient mathematical models that'll give you results that will allow you to understand whether something's possible or impossible, that kind of thing. Anyway, the model is point particles interacting via exchange with other point particles. In other words, the model is as simple as it could be. Well, it's not really. The standard model certainly isn't. It's got all kinds of bizarre crap in it, and it's all tied together in bizarre ways. When one applies quantum theory to the model, a dual description involving fields can also be used. Yeah, well, whether you call it a field or a wave is probably pretty important. And I'm not opposed to this idea of a field, but I'm still going to argue that a field is made out of something. And so that's what really hasn't gotten modeled yet. And I think it's probably there to be done if the right persons are working on it. I don't think there's enough, unfortunately. There's no money probably in theoretical physics, so the only people doing it are people in bizarre circumstances where they're allowed the luxury of doing it. Most people have to earn a living by actually producing something. So anyway, so we'll move on. But again, I'm not against quantum mechanics. So let's understand one of Feynman's key contributions here is this idea of time. Okay, and I would argue time equals distance. The two are you can't separate the two when it comes to a photon, because it's always moving at the speed of light. So if there's any change in its distance, there's a change in the time of its arrival at any particular point. And so what's happening with light is light can travel in paths that vary from a same starting point. It can travel in a straight line, it can travel in a not straight line, and what you're going to have at this point are two different particles. Based on how long it took them to get to a place, and what happened to them in getting to a place. So I would argue. So in the background, there's just I couldn't get any good. I did do the 2-slit thing with you know, needles and a laser pointer, and the results were okay. I mean, you got the bar pattern, but you got bars that went really a long way out, which isn't like the standard images you get of just 2 or 3 bars and then they fade away rather dramatically. But it was an interference pattern, you could say. But I also got it by just using polarized filters and a laser pointer pointed directly into the camera. You get the circular wave patterns, which essentially we're arguing are the same patterns. They're the same phenomenon, just abstracted in a different way. So let's see, which points do I want to get to? So we know that light has a feature, this polarization thing. So here's the 3 filters I used, and we know that if you do the 2 filters crossing each other, you're going to wipe out light, all light, and but that you can do this erasure kind of thing, where if you have one filter at a 45-degree angle in between the 2, that you will preserve the light. Polarized light will be essentially bent by the second filter, and then it can be bent another quarter turn by the next filter, so you will retain the light. It doesn't work on reflected light, so everything just blacks out on reflected light. Now if this wasn't just reflected light coming back up, what you'd see here is that these patterns at the angles would be very dark, and this stuff in the middle would be very light. And polarized light's working like that. So we know that light's polarized. So that's one fact we have about light, is that it has some sort of shape. You could go, it's you know, it can fly in these 2 configurations. And a polarized filter is basically just bars like a prison cell, and the light can get through the bars. If it's in this configuration, it can't get through the bars if it's in this configuration, and you know, and obviously if it's in some degree of configuration, some half configuration, or the bars are in the half configuration, it can slide through the bars. It can be bent into, it can be polarized by the bars. It will be changed by the bars. Alright, we also know that this stuff has a thickness, and so the light traveling through even these filters is going to be, some of it's going to go through at different speeds based on the path it takes through the filter. So I think these are safe statements. I would argue that this originated as a way of getting rid of glare, and the reason why I got rid of glare is that glare is truly reflected light. It remains polarized by the sun, and so I guess I would argue that sunlight comes down, and when it reflects this glare, it's a pure reflection, which means it's bouncing, and when it comes off as a color, it's really new light. So the photon goes in and a new photon comes out. So colored light, light that is a color reflecting off of an object, all of these photons I'm seeing are not the sun's photons. They're photons being created because the photon comes in, hits an electron perhaps traveling around an atom, and the electron produces a new photon. So a photon comes in, electrons produce a new photon of a specific color out. And so this is an interaction, and this interaction will obviously slow down the process of the speed of light. So obviously if light light that would bounce off a surface would certainly be moving faster than light that interacted with the surface and then left. So there's always a twist or a turn, you could say. With each interaction there's a twist of time. So if we say we can accept that light has obviously one property called, it can be in this configuration of being polarized. So all we have to do to explain quantum mechanics, to explain the wave theory, the probability theory of quantum mechanics, is accept that light has some other property. And that I would argue that that property could, like the marks on a clock, could have standard they could be rigid, a digital kind of effect. So it's in a state, state 1, state 2, state 3, and these could be considered energy levels. They can consider whatever you want to consider them. But as time passes, with each click of the clock, they move into a different state at a consistent level, a rate. So if they start off at a point, all being at 2 o'clock on the clock, and they move through some sort of interaction, some sort of field, some sort of thing, and they do it just slightly differently, one of them will arrive at the target slightly sooner or slightly later, but they will arrive at the target in a different state because their clock has gone further through time, and so they will be in a different position. So if the arrival point is something like the two-slit experiment, and these photons are arriving at these slits at different times because they take a different path to get there, especially the way the experiment's usually configured. You're talking about a gun that spreads photons in erratic fashion. There is no laser shooting of the photons through the slits. It is merely a pattern that's reduced through filtering to create photons that, generally speaking, will have a pattern that can get them to these slits. But they can get to these slits through different routes, and so be at different clock points when they arrive at the slits, and based on their clock point they will react with these slit material, the walls of the slits, differently. It's like them almost having a different mass or some other different configuration. It's like having pool balls and having them through time change their density or something. How much they are capable of transferring their energy. And so you could argue that if the two were in exactly the same state, they would reflect in they would be deflected in their path a certain angle based on their mass. But if they're at a different clock tick, they'll deflect differently based on that change in their configuration, how they're going to interact. And the whole function of the two-slit experiment, let's understand, is that it's designed to maximize the amount of interaction between the photons and the slit material, the walls of the slits. It's designed to limit this space in between the slits so much that it's likely the photon is going to react with the impediment material as it goes by. And so that's why I think you get the effect you get. Now, the thing with the two-slit experiment that is the phenomenon they haven't explained and all that stuff is that when you send these single photons... Alright, battery buggered out on me. Yeah, I don't know how long this one's going to last either. But whatever, we'll go for it. So anyway, wherever I was, so I was somewhere in this two-slit and the maximizing interaction between the slit material, and that's what creates the pattern. And then when they send single photons, they're obviously duplicating the same. They'll have the same kind of erraticacy in terms of the time they reach the slits and all of that stuff. So I think the phenomenon is something built into the photons, not built into the experiment itself. And it's not a wave interference pattern in the sense that two waves are interfering with each other in any kind of classic way. What's interfering with each other are the time changes in this clock of the photon itself, and the fact that the photons are in a different state. And so it's the combination. It's like at a roulette table, you could have different factors or dice. You have how the dice are rolled, what surface they're hitting. You can have different variables that will decide how the dice will end up displaying. And what there are is there's different variables in the condition of the photons as they interact with the two slits based on how they're produced, the fact that they would travel very eccentric paths that would create big differences in the distances. I mean, obviously you could say that there's a huge difference in, say, a photon that would reflect off of this surface and then bounce all the way over here to create an arrival way over there, or the photon that took this other path and looped around this surface, this corner. So you could say there was two different kinds of reaction. Those reactions where the photon's path is bent, and those reactions where the photon's path is refracted. And that there's all these variations in between based on what position the photon arrives at the slit at, and based on what path it took to get to that position. So you have the position when it arrives at the slit, and you have the condition of the path it took to get there. And those two conditions, I mean, let's understand too, the original two-slit experiment, as I understand it, used another slit to filter the light. So the light was filtered by a slit that was in fact probably changing the direction of light already. So that was creating the phenomenon of the light's character, in terms of it there being a possibility of the photons having taken a different path from their creation point at the source. They were forced through a slit and then forced into a two-slit experiment. So this original slit may have already created the change, the distinction. So if these photons theoretically came out exactly the same, on exactly the same trajectory, there's no way they could pass through these two slits in any kind of random way, because they'd always hit the center of the target. We should have a perfect beam of photons. So it's only by scattering the beam, scattering the light, that you can create this experiment in the first place. And I would argue that it is that scattering that creates this change in clock position, which creates the change in, I'm not saying it's a function of energy, but I'm saying think of it as a level, or a reactive tendency, or whatever you want to call it. But it's a condition like polarization that is a physical condition of the photon that is now changed because it has moved through more time, it has traveled more distance, and therefore is in a different condition when it reaches the slits. And it is that variable combined with the variability of where they can arrive at the slit in what condition. Those would be the two factors, and that would be accounting for the different arrival points probabilistically. Because now you have these two variables creating an arrival point. So anyway, that's probably enough for this video. I don't want to beat it to death, but I think these are real properties of the physics. And I think Feynman's, the use I've gotten, the new use, is this idea of understanding what Feynman was saying by saying cycles of a clock. And by saying that, he's basically just saying that each photon can go through many, it can go for each 1 trillionth of a second or whatever, 1 zillionth of a second, there could be one of these clock cycles, and that so any change in time is going to leave the clock hand in a different position for the photons. So even though they start off at the same place, it doesn't take much of a change in their direction to change dramatically their condition, one being a 6 o'clocker and one being a 3 o'clocker, because they are on an internal cycle that started off the same but will change through change in distance, like hitting like the lens example. The light going through the thickest part of the glass will take longer to get through, and the light traveling through the thinner part will have a shorter. But the other phenomenon is the path is longer. So I don't know which effect is more dramatic, the longer path or the amount of material the light has to travel through. But it doesn't. The point being is that it's the differences, and what happens to the light is a function of these conditions here that are already created differently. Yeah. Well, anyway, something like that. So, till next time, and such. Take the next step, whatever that is. Yeah. Alright. Yeah. Good enough.